let's start our second plenary talk of this conference, given by Patricia Hersh. She's a professor from University of Oregon. She graduated from MIT, and her supervisor was Richard Stanley. She's an expert in algebraic combinatorics and topological combinatorics. She won, in 2010, she won the Luz Michler Memorial Prize of the Association for Women in Mathematics. And in 2015, she was elected as a fellow of the AMS. So today, she's going to talk about the process arising as one skeleton of simple polytopes, the non-revisiting path conjecture, and poset topology. Please.
Thank you. I'm delighted to be here. It's a very nice conference. Yeah, so as he mentioned, one of my main areas is poset topology, and I'll review various things related to all these topics. But you know, sometimes research goes in unexpected directions, and I started discussing some poset topology question with Carola Mesoros and some other people, and things just somehow wandered over to some questions about polytopes, and I became really fascinated by trying to get polytopal techniques to interact with poset techniques, and kind of find a best of all possible worlds for certain classes of polytopes that are connected to posets, where maybe you can say a little bit more than you can about a lot of other polytopes. So this is not a joint project with Carola, but I want to thank her because in the early part of the project, I benefited a lot from talking with her. It ended up that we've written a different paper together, but this definitely benefited also from her contributions. Okay, so our starting point is actually linear programming. A lot of the interest in, I'll say what a polytope is in a minute, but a lot of the interest in polytopes comes from connections to operations research and linear programming. And let me explain what the basic problem is there. Probably a lot of people have heard of the traveling salesman problem. That's an example. Given an m by n real matrix A, and here we have an example that's a 3 by 2 matrix. You can see just in the kind of lower left of the left slide. So m is 3 and n is 2. So you start with a real m by n matrix. You start with a real vector B in Rm and a real vector C in Rn. And what we're looking at is we're looking at all possible vectors x in our n, so n equals 2 here, number of columns. You're looking for all possible x such that if you take a times x, the product coordinate-wise is less than or equal to the vector b. So b is fixed. So here, this would say negative x. So the first row times the column vector would say negative x1 is less than or equal to 0. And then negative x2, the second row times x says negative x2 is less than or equal to 0. And then the third row times x says x1 plus 2x2 is less than or equal to 2. So we're looking at all x's that satisfy a system of inequalities like this for our fixed a and our fixed b. Okay, and the set of such x is a polyhedron, and if it's a bounded set, it's a polytope. It's called a polytope. It's some subset of Rn, and then what we do is for our fixed vector c, we look at all the points in our polytope, all the x's that satisfy the inequalities, and say which x has largest dot product with c, or sometimes we want to say which x has smallest dot product with c. And I've drawn an example down here, and this is the actual inequalities we get here, right? We have saying negative x1 is less than or equal to 0 is the same as saying x1 is greater than or equal to 0. So we have this vertical line, and we're only looking at points to the right of it. We have x2 greater than or equal to 0, so we have a horizontal line, and then all the points above it. And then we have x1 plus x2 less than or equal to 2. And then that means we have this line, and we look at only the points down from it. And the intersection, the set of points that satisfy all three inequalities would be the intersection of these three, quote, half spaces, and it'd be this closed triangle, right? And now what we do is we have a cost vector And I guess I didn't write a specific cost vector, but I drew an arrow here. Imagine it's a vector like that. So that looks like something like 2 comma minus 1. Then for each point in our polytope, we take its dot product with C and figure out who has which dot product, where do we get the biggest dot product with C. And if you think about it, if we draw lines in this case, or more generally hyperplanes, perpendicular to C, those will all the points on a hyperplane will have the same dot product with C as each other. And as we sweep across like this, we'll get bigger and bigger dot products. And the maximal dot product will be at this vertex of our polytope. And the point of linear programming is to figure out which point in the polytope has the biggest dot product or the smallest for your given A, B, and C. Okay, now this relates to combinatorics, especially by looking at the graph of our polytope. That's going to be just the vertices and the edges. So here I've drawn a little bit bigger polytope, a 3-dimensional polytope. You can see how you'd have it's an intersection of half spaces and it's bounded. Okay, and all right, so now so we could talk about its graph, just the vertices and the edges of this. And then we're going to let G of PC be a directed graph on the one skeleton of P. So on the graph of edges and vertices, where we put an arrow on each edge in the direction that the cost is increasing. So the dot product with C here is getting bigger, okay? I mean, you might have a tie, but we're always going to use generic C where ties don't happen. So if you pick C in a random direction, it's not going to be perpendicular or whatever to any of the lines. And so there won't be an issue of ties. So, okay, anyway, so we have this directed graph. Now the simplex method is an old famous method for solving linear programs. And what it basically boils down to is you take some vertex, you start at some vertex of the polytope, and you just greedily walk in the direction that arrows are increasing or that arrows are going. So if you're like at this vertex, you have more than one choice, but you just pick one and walk, and then you pick an arrow away from here and follow. And sooner or later, you get to the unique sink of the polytope where you can't walk any farther, and that'll be where the dot product is maximized. So that's the simplex method. And then, but you can see then that a key question in terms of how efficient it would be is how long are these directed paths, right? Oh yeah, and a famous example is the traveling salesman problem that, say you have 4 cities, V1, V2, V3, V4, and roads between them of these various lengths. You want to know what's the shortest circuit that visits each of the 4 cities and comes back to where you started. So there's the green circuit, or there's the purple circuit, or there's the blue circuit. Okay, and for each of them, the cost would be the total distance traveled, the sum of the edges. We can turn this into a linear programming problem by making a polytope whose vertices are vectors of 0s and 1s, where for each circuit you have a 1 for the edges that are in the circuit and a 0 for the edges that are not in it. So I've just named think of this as this would be E12. These are in lexicographic order: E12, E13, E14, E23, E24, E34. So the edge from EIJ would be edge from I to J, and you put a 1 if your circuit involves an edge from VI to VJ. So we have the green approach, the purple, or the blue. And then if you think about it, for each of these circuits, the cost of that circuit is the dot product of that vector with this cost vector that has all the edge lengths. And right, and so what we're looking for, I guess in this case, we would want to minimize the dot product, the point in this polytope that minimizes the dot product. So anyway, so that's an example. And there's lots of real world problems that can be phrased this sort of way. Okay, and just to formalize, so we're going to study we're going to ask what properties of polytopes could allow us to say more about the efficiency of the simplex method than you can do in general. So let's see. So a polytope is a subset of R to the D that's the convex hull of a finite number of vertices, or equivalently, it's a set that it's an intersection of half spaces that happens to be bounded. Sorry, I have to drink water, it seems. Now, okay, here's going to be a key property for what we're going to do. We're going to focus on what are called simple polytopes. If you these are quote unquote dual to simplicial polytopes, which are ones whose boundary are triangulations. But here's the definition of simple polytope that'll be really useful for us. When a polytope is simple, if for each vertex and each set of edges emanating out from that vertex, like say we have here 4 edges emanating out from the vertex, for your polytope to be simple, we want to require that there does exist an r-dimensional face using all of those using all of those edges, okay? So for example, this vertex V here satisfies our requirement. If you take E1 and E2, those edges, sure enough, there's a 2-dimensional face, or E1, E2, and E3, there's a 3-dimensional face. But like this polytope here is no good, because if you look at the vertex V, and say you take this edge and you take the opposite edge over here, what we say is that there should be a 2-dimensional face of the polytope containing both those edges. But there's not, because I guess I didn't define face, but if you look at like the smallest 2-dimensional region that contains those 2 edges, that cuts right through the middle of the polytope, and a face should be something on the exterior. It's the intersection of the polytope with what's a bounding hyperplane. So anyway, this is not simple because of the fact that you can maybe intuitively think that this over here looks like a 2-dimensional face. Back here looks like a 2-dimensional face. Clearly there is no 2-dimensional face cutting through the middle, okay? There is a 2-dimensional face up here with these 4 vertices. So anyway, this is not simple, this is. So we're gonna want simple polytopes. Now in linear programming, people talk about pivot rules, and what a pivot rule is it's some kind of rule to decide when you're walking along in your directed graph trying to find the sink. If you're at a vertex V and there's more than one edge going out from it, how do you decide which one you should use? Maybe you use the one that seems to increase the cost the most, or maybe you have some other strategy, but a pivot rule is a strategy for deciding, okay? So what's your best path to go? And it's not obvious what should be the best pivot rule. So key questions would be, what's the typical complexity of the simplex method, and what's the worst case? So let's say by complexity, we mean the number of edges you have to traverse to get to the sink, okay? And this is clearly related to the diameter of the polytope, where what diameter means here is for any pair of vertices, you can say what's the distance between those vertices, and that's the fewest number of edges you need to traverse to get from one to the other. The diameter of the polytope will be the biggest possible distance between any pair of vertices, figure out which 2 vertices in the polytope have the biggest distance or farthest apart from each other in the sense of distance, and that'll be the diameter. Okay, so people in geometric combinatorics have done a lot to study diameters of polytopes and also these kinds of directed diameters on this directed graph. And a big question that was open for a long time, although eventually a counterexample was found, was the Hersh conjecture. And this is not spelled like my last name. Victor Klee devoted practically his whole career to this, and it got all kinds of interesting results related to it. Oh, oops. So here's the Hersh conjecture. Given a d-dimensional polytope with n facets, and a facet is a maximal face. I don't mean the interior, I mean among the boundary faces, the highest dimensional ones. Okay, so n is the number of maximal boundary faces, d is the dimension. Then the conjecture was that the diameter of the one skeleton of the polytope, the undirected diameter, denoted delta dn, should be less than or equal to n minus d. So less than or equal to the number of facets minus the dimension of the polytope. And after many decades of this conjecture being open, and many people working on it, Francesco Santos constructed some beautiful counterexamples using a notion called spindle. And a spindle is a polytope with two vertices V and W, such that every facet of the polytope either includes V or includes W. So pictorially, it looks a little bit like this, kind of like this top or something. Okay, but his first, there are smaller counterexamples now. His first counterexample was 43-dimensional with 86 facets, where he could prove the diameter was at least 44. So that was bigger than 86 minus 43, right? So, okay, so anyway, so the Hersh conjecture is not true in general, but I started to suspect some conditions on a polytope and on the cost vector C that might allow the Hersh conjecture and some related stronger conjectures to hold. So since it's not true in general, I want to talk about some conditions where one thinks it may hold. And I have a kind of exciting announcement at the end. Yeah.
Patricia, can I just ask you, is that the smallest counterexample?
No, there have been subsequent ones that were smaller. That's just the first. And I don't remember how small they go, but they're pretty big, but they've gotten a lot smaller.
Thanks.
Yeah. Okay, so a related conjecture, which is actually ties in much more with what I'm talking about, is the non-revisiting path conjecture. Now, and this is something that when you first hear it, you easily might guess it might be true, but lots of things about polytopes that sound like, oh yeah, sure, that's true, are just not true. But it's pretty easy to prove the non-revisiting path conjecture implies the Hersh conjecture. So now that there's a counterexample to the Hersh conjecture, there's also a counterexample to this, right? But here's the non-revisiting path conjecture. For each U and V in a polytope P, there exists a path from U to V that never revisits any facet that it has left. Okay, so I think I need to go to an example to explain that. Let's see. Yeah, so let's look at this polytope here, this cube, right? So say you're at the vertex 0, 0, 0, and you take this edge to 1, 0, 0. The vertex 0, 0, 0 belongs to this facet over here, right? But when you take that edge, you depart from that facet. So what the conjecture says is that when you look at these directed paths, you never have to like revisit a facet you've left. So once you leave this facet, you're not going to have to come back around here and come back to it. Okay. So now that I've explained that, so what it says, for each U and V in the polytope, there exists a path from U to V that never revisits any facet it has left. So every time you traverse an edge, you're going to leave a facet because there's like a whole bunch of facets that contain that vertex, and that edge, if you think about it, there's going to be at least one of those exactly, I guess it's, yeah, well, let's say at least one of those facets that it leaves, okay? Anyway, so, and the way you see the implication is that if you did have a non-revisiting path, that at every step it leaves a facet, right? So right away from there, you know that the number of, if you never come back to any facet, then you only had n facets. And so there can be at most n steps because each step has to leave a facet and there's only n facets available to leave. But if you think a little bit more carefully, you realize at the end of the day, you'll be at a vertex and we're in a d-dimensional polytope. That vertex is going to be contained in d facets. So there's d facets that you're not allowed to leave because you're in them at the end. So in fact, there's at most n minus d facets you can depart from, which means at most n minus d edges in your path. Okay. Oh, so I misstate, I put the wrong name on this conjecture if I see when I wrote the slide. This should be the monotone Hersh or strict monotone Hersh conjecture. I don't know why I wrote this, but what it says is, this is another related conjecture that's also not true, that there exists given a polytope P and a cost vector C, there always exists a directed path of length less than or equal to n minus d from any vertex V to the one from any vertex to the vertex that maximizes the cost. And in fact, where the directed path increases cost at each step. So this is saying if you're anywhere on the graph and you start following arrows, you can get to the sink in at most n minus d steps. So this also is false, because if there's a polytope of too big diameter, you can construct counterexamples to this. Oh, thanks for fixing that. So our plan is to suggest what somehow I stumbled on what I thought were good conditions to impose upon a polytope P and a cost vector C that would imply lots of things, including, and we'll prove some of the things it would imply. But, I want to impose conditions on P and C that will imply, that which I conjecture would imply the following, and we can prove it implies some related things. So I conjecture for the P and C, we're going to, for the condition, for the conditions we're going to assume on P and C, that our polytopes and cost vectors will have the property that for each U and V vertices in the polytope, not on every possible directed path from U to V has the property that it never revisits any facet it has left. So this is way stronger. This is not just saying there exists a directed path from U to V that never revisits any facet it has left, but no matter which way you go, following the arrows, you're never going to revisit any facet you've left. So this says that every possible directed path to the sink uses at most n minus d steps. It doesn't even matter which pivot rule you use. So we want to suggest what we think conditions on P and C would give this really strong condition. And we'll prove some corollaries of this for our conditions, okay? So like I said, this property here would make all possible pivot rules efficient for any polytope P and cost vector C that satisfied our conditions. So now I want to describe what conditions we're going to use. And I'll say right off, for P, we're just going to assume that it has to be a simple polytope. So that's why simple was important. And then we're also going to assume some things about the graph G of PC. Okay, so all right, that leads us to, this is going to be one of the two big things we're going to assume about the graph G of PC, that it be what's called a Hasse diagram. And that's going to lead us into posets. Okay, so we'll say that our directed graph G of PC has the Hasse diagram property if it is the Hasse diagram of a finite poset. And what that means is that whenever you have a directed path, V1 goes to V2, goes to V3, to VR, where R is at least 3, so where we have at least 2 edges, then there is not also a directed edge straight from V1 to VR. So we're disallowing pictures like this. See, what a Hasse diagram is it shows the minimal cover relation, you can think of the arrows as giving us all the less thans in a partially ordered set, but they're only giving us the ones that are not implied by others, right? If V1 is less than or equal to V2 and V2 is less than or equal to V3, that transitively implies V1 is less than or equal to V3. So in the Hasse diagram, you only write the arrows that are not implied by the others. So we're interested where our one skeleton with the arrows, how cost increases, don't allow any of these shortcuts, okay? Now, sadly, there will be a bunch of polytopes and cost vectors that satisfy this, but right away we rule out a huge class that I'm very sad to rule out. We rule out polytopes that have any D simplices, any faces that are just simplices for D greater than or equal to 2. Because as soon as you have a triangle and put arrows where you don't allow a directed cycle, you're not going to have there won't be any directed cycles if you're going in the direction cost increases, right? And as soon as you put 3 arrows where you don't have a cycle, you're going to have one of these shortcuts. So we rule all of those out. But what I will say is that this Hasse diagram property is equivalent to our non-revisiting property for one-dimensional faces. So it says exactly the same thing as we never have a directed path that leaves an edge and comes back to it. So, because we couldn't come back to the same vertex, that would be a cycle, and we don't have directed cycles. So this would be a necessary condition for the kind of thing we want to do, but it's almost sufficient. A technical note is that our posets that we're going to look at the poset. So we're going to think about these G of P as being Hasse diagrams of partially ordered sets, and then that'll allow us to use poset-theoretic techniques to study them. And I just want to remark that quite often these posets will not be quote unquote atomic, whatever that means. Now, a first example would be a hypercube polytope. So here's just a three-dimensional cube, and I just put arrows in the direction that, where you change zeros to ones, this unit cube. And that's consistent with this cost vector 1, 2, 3, right? The dot product increases along those arrows. And this is the Hasse diagram of a partially ordered set called a Boolean lattice, B3 or B1, 2, 3, the poset of, it's isomorphic to the poset of subsets of 1, 2, 3, of the set 1, 2, 3 ordered by containment, right? You could just think of this as the empty set, this is the full set, and your subset is saying which positions do you have ones in. So this is clearly an example. Okay, now I want to show an important an example of one of these directed graphs that is not a Hasse diagram. They're called the Clementi Cubes, and these are important because Cle and Menti found these as the first example of polytopes where the simplex method does not work well, where it's not efficient. And so it's a good sign that the polytopes where the simplex method is not efficient would be ones that violate our Hasse diagram property. So here's a picture of a Clementi cube. What you do is you take a standard cube, but then you move the vertices around, right? And we take the convex hull. So we have a vertices. I've written, I guess it's tiny, but the actual coordinates, but we have these vertices. Here's a description of this as in terms of the inequalities. So you can think of it as an intersection of half spaces, that the x1 coordinate, which is along this axis, just ranges from 0 to 1. And once you pick x1, you fix some epsilon that's between 0 and 1/2. In this example, I've used epsilon equals 1/3. And then for the next coordinate, you say whatever the first coordinate is, the second coordinate has to be in between epsilon times the first coordinate and 1 minus epsilon times the first coordinate. So in this example, x2 has to be greater than or equal to 1/3 of x1 and less than or equal to 2/3 of x1. And that gets this back face here, you can see, and so on. And anyway, it looks like this, but then the key is that if our cost increases as the x3 coordinate increases, as the height increases, then we're going to have a directed path that goes like this, right? That's a really long way of getting from here to here. There's a shortcut just taking this edge, but this directed path clearly departs from a one-dimensional face and comes back to it, so it violates the Hasse diagram property. But in fact, it violates it in a smaller way right here on this little face, right, on this green face, because you could have cut straight across here instead of going around like that. Anyway, but this shows the Hasse diagram property at least rules out the Clementi cubes. Okay, so yeah, and our hope is that if you have a simple polytope with the Hasse diagram, and G of PC is a Hasse diagram, perhaps that's actually good enough to buy you a lot of things. But in terms of proving things, we actually assume a little bit more that gives us more to work with. But before I get to that, let me tell you a couple of examples. The permutahedron, and what time do I end? I forgot.
You have like 20 minutes more.
Okay, thank you. 12:30. Excellent. Okay, good. So a couple of nice examples. If you take the permutahedron, so in Rn, this is the convex hull of all the vectors you get by writing the numbers 1 through n in the various orders. Okay, so it's a beautiful polytope. And if we use as our cost vector the vector 1, 2, 3, 4, then down here, the 4, 3, 2, 1 is going to have the smallest cost. It'll be 20. 1, 2, 3, 4 has the largest cost. That'll be, I'm sorry. Am I doing this right? Yeah, I think so. 1, 2, 3, 4 has the largest cost. That'll be 30. And you go up by switching to neighboring coordinates in a way that increases the number of, or I guess the way I've drawn it decreases the number of inversions. But anyway, this is the weak order or dual to the weak order, the partial order we get here. And I want to remark that for this poset, the weak order, it was proven by Edelman in type A and Anders Björner more generally that every interval in this poset, if you take a simplicial complex I'll discuss later called the order complex, that'll be homotopy equivalent to a wedge of, to either a ball or a sphere. And we'll get a new proof of that from some more general context later in the talk. But a second nice example is a polytope called the isociahedron, using a realization of Lode. In this polytope, the vertices are binary trees, and our cover relations, the edges of the Hasse diagram, are given by little local moves that look like this, where you switch like parenthesizing like that to parenthesizing like that. And again, this will be a poset, and it'll be the Tamari lattice, another famous poset. And the homotopy type of the intervals in the Tamari lattice were determined by Björner and Wax via non-pure shellability, and again, each shown to be homotopy equivalent to a ball or a sphere, and we'll recover that from our results later too. You know, I mentioned to you, we started in poset topology and then wandered into this other stuff, right? So we'll circle to that towards the end. Now, here's just a lemma to give a flavor for, so now I guess I could say that, well, I'll go ahead and say that what I believe is that if you have a simple polytope and then P, and then your graph G of PC is a Hasse diagram, and my conjecture is actually for not just a poset, but what's called a lattice, and I'll discuss that later, then every possible directed path from U to V from any vertex U to any vertex V will have the property that it never revisits any facet that it's left. And that implies all sorts of versions of the Hersh conjecture for these polytopes and cost vectors. So we'll come back to that. But here's a lemma that I'm including because it has a really simple proof, and it starts to give a flavor of what having a simple polytope and a Hasse diagram buys us, okay? So given a face F so this purple thing here, this example is two-dimensional, contained in a face G of your polytope that's one dimension bigger, so three-dimensional here, all within a simple polytope P, and given a generic cost vector C, such that our directed graph is a Hasse diagram, then for any pair of vertices V and W in our face F, like our purple face here, it's not possible that we have, on the one hand, a directed path from V to W that stays entirely in the lower dimensional face, and on the other hand, an outward edge from V that goes into the portion of G that's not in F, and an inward edge that goes into W from the portion of G that's not in F, okay? So this in particular, this would rule out the possibility of, on the one hand, having a directed path from V to W that stays in F, and on the other hand, having a directed path from V to W that exits and comes back, right? So, and the proof of this is really simple. What you do is, because it's a simple polytope, for each of the vertices along this path from V to W, this path in F, there will be a unique edge adjacent to that vertex that is within G but not F. So it like exits to the portion of G that's not in F. Each of those edges either points out or it points in. Okay, so if you start out pointing out and you end up pointing in, and you have a series of outs and ins, at some point along the way, you have to switch from out to in, right? You'll have two consecutive edges where one goes out and the other goes in. I mean, you could switch back a few more times, but in particular, at some point you'll switch from out to in. And then we can prove that this edge and then this out edge and this in edge all live in the same two-dimensional face. And within that two-dimensional face, this vertex here is the source, this vertex is the sink. There's this edge from the source to the sink, and there's a directed path going like that from the source to the sink. And voila, you violated the Hasse diagram on that two-dimensional face. So anyway, so this is kind of encouraging that you could kind of propagate up in dimension, okay? And a corollary of this is that for each face F of our polytope, if the face contains the overall source of, the overall source of the polytope or the overall sink of the polytope. So if F either contains the source of the polytope or F is up here containing the sink of the polytope, then there cannot possibly be any directed paths that depart from F and then revisit F, okay? So anyway, so that's helpful. Okay, now I'll give the promised definition of what's a lattice, since for our big conjecture, we need that. A lattice L, a poset, a partially ordered set L is a lattice if for each pair of elements U and V in the poset, there's a unique least upper bound, a unique thing bigger than U and V that such that every other upper bound is less than the, is greater than this. And we'll denote it like this. And a unique greatest lower bound, a unique biggest thing that's less than both of these, we call the meet. Okay, and we denote like this. I like to think of these as like union and intersection from the case of subsets of 1 through n, of the poset of subsets of 1 through n. But anyway, a lattice is where you have a join and a meet, these algebraic operations. Now, notice if P is a simple polytope and G of PC is a Hasse diagram, let's say we have an element X and we have arrows from X to U and X to V. And then because it's a simple polytope, there's got to be a two-dimensional face that contains both these edges. Well, and there will be a sink to that face, that has only in arrows to it. Now I want to just observe that sink will be an upper bound for U and V, okay? So it's not necessarily the least upper bound, but then the big, there could be some other upper bound that's smaller somehow outside this face, but this will be an upper bound. Okay, this leads us to a definition we call the pseudo-join in a polytope. So given a simple polytope P with a generic cost vector C such that our directed graph is the Hasse diagram of a poset L, so I'm just saying poset right now, with x1 through xr elements of L, such that there exists so we start, this is just set up so far. Okay, so we have P is a simple polytope, generic cost vector C. This is a Hasse diagram of a poset. And then suppose we have an element U and a bunch of things that cover U. So a bunch of things that we follow arrows from U straight away to those. So x1, x2, xr, there's arrows from U to each of these, okay? And and this notation here is just poset-theoretic notation for saying there's an arrow from U to V in our Hasse diagram. So U is less than V with no intermediate Z, okay? It's called a cover relation. And in AI, we also want the notation that AI is said to be an atom of the interval from U to V. This closed interval is just the set of things that are greater than or equal to U and less than or equal to V. So that'll be a subposet. The atoms of this are the things that cover U, the things where you have arrows from U to them, but they're less than or equal to V. Okay, now that we have all this set up, we'll say that the given x1 through xr that all cover the same element U, we'll define the pseudo-join of x1 through xr to be the sink of the unique r-dimensional face of our simple polytope that contains all these edges. Okay, so going back a slide, S here would be the pseudo-join of U and V. We don't know yet if it's the join, but it's the kind of geometric analog of a join, what we might hope might be the join of U and V. Okay, so in this polytope here, if we have this U, this x1 and x2, this is the pseudo-join of x1 and x2. Okay, and one of the things I was speculating is for lattices that the pseudo-join would actually equal the join. And we do end up proving that. So since the pseudo-join of x1 through xr is an upper bound, we know there has to be a directed path from the join of x1 through xr to the pseudo-join, because the join has to be less than or equal to every other possible upper bound for x1 through xr, and this will be an upper bound. But whether they're equal was not obvious. And it took like years actually for me to prove this. Maybe somebody else could have done it faster, but I found it pretty challenging, the next theorem. So let P be a simple polytope and C a generic cost vector where G of PC is the Hasse diagram of a finite lattice. Then the pseudo-join of x1 through xr actually is the join of x1 through xr. And I'm definitely not going to discuss the proof, but I'll just show you this picture to give some inkling of the case, actually for two-dimensional faces. I just want to give an inkling of what the issue is. So here, if we have this U covered by X and Y that both belong to this two-dimensional face, the thing we're worried about is maybe there's a directed path out of the face over here and another directed path from Y out of the face that both come to the same spot, and then a directed path that comes back in to V, right? So we want to rule that out. And that looks that would be an example, a type of that would be an example of a path that departs from a face and comes back to it, right? So this all ties together, right? So this theorem, this theorem seems relevant to try. If we had this kind of non-revisiting of directed paths, it would imply this theorem, but the non-revisiting of paths is just a conjecture at this point. But okay, now I'm going to quick switch gears to poset topology as promised. And then I want to conclude, as I said, with some kind of exciting announcement that I learned about. Somebody proved a corollary of my main conjecture that's, I think, pretty exciting. So anyway, so the order complex of a poset is the abstract simplicial complex whose I-dimensional faces are the chains of I+1 comparable elements in the poset. So here's an example. Here's a partially ordered set. And so the elements of the poset give us vertices of the order complex. Whenever you have U less than B in the poset, that gives us an edge. So 0 hat is less than B2, so we have an edge from 0 hat to B2. 0 hat less than B1 less than B2, that's a triple of, of things, each of it, a chain, a two-chain, or sorry, a three-chain of things, one each less than the next. That gives us a two-dimensional face. So we get this simplicial complex, and there's a lot of interest in these because the Mobius function of a partially ordered set is useful for calculating by inclusion-exclusion. It gives you the coefficients in inclusion-exclusion formulas, but that was actually proven a long time ago to be equal to the reduced Euler characteristic of the order complex of the subposet of things strictly between U and V. So this allows you to study the topology of this, and reduced Euler characteristic is -1 plus number of vertices, minus number of edges, plus number of two-dimensional faces, and so on. And you can calculate it via Betti numbers too. Actually, I'm going to skip this fact. But let me say the Quillen fiber lemma, that's going to be a key technique for what we're going to do with poset topology here. Given a finite poset, or given a poset map F from a finite poset P to a finite poset Q, such that for each element Q in the image poset, if you take the order complex of the subposet of P of things that map either to Q or something below it, let's see that, what am I saying here? Oh, that's just the definition, that if each of those order complexes of these subposets are contractible, then that implies the order complex of P is homotopy equivalent to the order complex of Q. So basically, this is conditions where you can, if you understand the topology of P, of its order complex, you can deduce the topology of the order complex of Q, or conversely, okay? And this gets used extensively and has been used extensively in finite group theory, for instance, to characterize which finite groups are solvable or which finite groups are super solvable, among other things. And we're going to use this to prove the following theorem. For P, a simple polytope, so back to polytope, not poset. For P, a simple polytope, and C, a generic cost vector such that G of PC, our directed graph, is the Hasse diagram of a finite lattice, then for each interval, each U less than V in the poset, the subposet of element Z strictly between U and V, the order complex of that will be homotopy equivalent to either a ball or a sphere. And I'll just say that our method of proof is by Quillen fiber lemma, and it utilizes the fact that join equals pseudo-join. We also prove that if you look at the different subsets of the atoms of the interval, that for distinct subsets, they have distinct pseudo-joins and hence distinct joins, and that this subposet will actually be a Boolean lattice. Applications of this are we get a unified proof of the homotopy type of the intervals for the For weak order, by way of getting it from the permutahedron, for Tamari lattices that we get from associahedra, and for Cambrian lattices that we get from generalized associahedra. Okay, now to the big exciting announcement. To my amazement, about a month ago, I got email out of the blue from a high school student in Germany who said he had proven something I was kind of shocked by, and he had like a 2-page proof. And I read it and it was correct. It looks to me like the kind of proof somebody like Richard Stanley would come up with. But I want to quick tell you about this. So here's my conjecture, okay, that's in my paper. And then he proved a consequence of this conjecture that was really the main motivation for the conjecture. So the conjecture was that if P is a simple polytope and G of P comma C is the Hasse diagram of a lattice, of a finite lattice, then no directed path in G of PC ever revisits any face or facet it has ever left. Okay, that's my conjecture. This would imply the monotone Hersh conjecture, and he proved that. So here's what he proved, that for P and C as above, no directed path in our directed graph requires more than n minus d edges, where n is the number of facets and d is the dimension of the polytope. And it's a beautiful, simple idea, very insightful. So this is just quick, his by the way, and he's allowing me to put his theorem as a appendix to my paper. So anyway, so let me share this with you. Okay, so his first insight is that a vertex V in your polytope is the unique source of a facet of the polytope if and only if the vertex is either the overall source of the polytope or is what's called a join irreducible in our lattice, okay? So a join irreducible is an element of our poset of our lattice that cannot be written as a join of strictly smaller elements. Okay, so that's his first insight. I mean, the point is that, so the thing is that if you have a join irreducible in a lattice, there's going to be a unique cover relation leading up to it. And so that means it's going to have lots of arrows going out from it, and it'll be the source if it's, and as long as it's not actually, so right, so anyway, the sources of the facets are exactly the overall bottom element. That's going to be the source for d different facets or the join irreducibles. Second, when you have one of these directed paths, each cover relation, each arrow ui goes up to ui plus 1 in L has the property that ui plus 1 is equal to ui, the join of ui with a join irreducible. But the different cover relations all have to use different join irreducibles here. And so therefore, the length of the longest saturated chain, the longest directed path, is at most the number of join irreducibles in your lattice. But that's going to be the total number of facets minus the dimension, because we have we have two types of facets. We have d of them whose source is 0 hat, and then we have the other facets who one for each join irreducible, right? So yeah, so that's the, oops, sorry, that's the proof. Oh, and I have 1 minute to go. I mean, of course, these are claims that all require proofs, but I thought this was very insightful. I was kind of amazed. So it implies the monotone Hersh conjecture and the Hersh conjecture for simple polytopes where G of PC and cost vector C, where G of PC is the Hasse diagram of a lattice. I guess you can't really say it implies the Hersh conjecture because that would be only for P, but it implies the monotone Hersh conjecture. Anyway, okay, final questions. Does polytope being simple and G of PC being the Hasse diagram of a lattice imply no directed path can revisit any face it has departed from? So that's my conjecture. Again, just kind of repeat it again. And I also would ask about variations on the hypotheses. I don't know for sure if we need to assume simple polytopes or if we need to assume lattices, but these two things work really well together for proving things. They're good for proving things. And then finally, it would be interesting to understand the structure of posets of joins or pseudo-joins for non-simple polytopes too. Thanks very much.
Thank you. Okay, so are there any questions or comments?
Trisha, I didn't understand how is the topological result about the homotopy type of those intervals at the end? Is that related to the Hersh conjecture, the non-revisiting conjecture?
Yeah. Oh, I see. Well, I mean, I guess the proof, it's only loosely connected. Both of the fact that join equals pseudo-join is critical for both. But one thing else, so the other thing, and the other thing else, it's a critical ingredient to both parts of the story, but things wandered around. But what I will say is that now that we know, I mean, it's theoretically possible that you could say, well, for this polytope, we get a poset where the, let's see, the poset topology does not behave this way, and therefore we cannot have the, or sorry, what do I want to say? That, yeah, I'm getting confused how exactly I want to phrase this, but what I want to say is that I think there are situations where you could say if the poset topology is bad, then you've got to violate one of the hypotheses, and you could deduce that you don't have, that you're not, you don't have the non, that you're, this is not going to be like a good Hersh polytope or whatever. But right now I'm getting it mixed up, but you know, you could imagine using poset topology to say that, okay, let's just put it this way, that we cannot, because the poset topology is bad, we cannot possibly satisfy all of the hypotheses here. Oh, but I would say that it's a loose connection. It's maybe that things have wandered around. Okay.
Okay.
But you know, yeah.
I have a question, and you might have said it before, but in terms of what are the, is it known which simple polytopes and which C are the Hasse diagram of a lattice?
That's a hard question.
And
yeah.
what is known?
Oh, well, see, nobody else has ever looked at, like, I mean, I don't think anybody else has been like taking this perspective and like, yeah, I mean, it would be hard to decide, like, if, you know, for a P and a C, are you a Hasse diagram? I mean, that's a limitation here for sure. Mm-hmm. I mean, Lou Bellera gave me some suggestions in terms of the adjacency matrix and raising it to powers and things, but even to write down your whole graph is hard.
But I mean, like, do you know a class of polytopes for which this usually happens?
Permutahedra, associahedra, hypercubes.
And they work for all C or for generic?
No, I'm sorry, like there exists a C that they'll.
Okay. Yeah. Okay. And then it's it's unknown in general? Yeah.
But you know, I mean, once you get outside the realm, I mean, I've heard some, I'm not a polytope expert, I'm more a poset expert, but I've heard polytopes experts say once you get outside the realm of simplicial polytopes, coming up with very many examples is hard. If Marge Bayer, I don't know if Marge Bayer's here, but.
No, but I mean, the simple polytopes are just the duals of simplicial. So
well, that's true.
You know how to generate a lot, but who knows when they would have this property.
Yeah, like I wonder, what about cubical polytopes, whether anyone's looked at those?
But they're generally not going to be simple, right?
Oh, I see what you mean.
Yeah, I mean, I'm not claiming this is a huge class. This is, let's say this is the best of all possible worlds, and it's not the empty set because it includes permutahedra and associahedra and generalized associahedra. And I don't know how big it is, but we can, I mean, it's really sad it doesn't include simplicial polytopes. If Marge has any more suggestions or anybody else.
Yeah, it is.
Okay, other questions or comments?
I mean, I just have one more. Is what if you do small dimensions, like?
Oh yeah, that's a good point. So for 3 yeah, I mean, I can, for instance, I can prove, I didn't even think to say this, like it's pretty, So we have so our tools do give a proof of this conjecture of mine for all 3 polytopes that satisfy our conditions, and also for all spindles. So we can show that there's no, so that speaks to kind of to Christian, it's not exactly Christian's question, but it's related that, you know, if you had, I should say for all spindles where like these 2 special vertices V and W, one of them is your source and one of them is your sink. But basically this says that it's not possible to construct counterexamples to my conjecture via Francisco Santos's method, because that his things cannot possibly satisfy all my hypotheses. Most likely they're not Hasse diagrams.
But spindles aren't going to be simple.
Right. That's or maybe I mean switch to the dual of spindle, but yeah, maybe I misspoke. So yeah.
What's the name of the high school student? I'm sorry, I couldn't quite make it out. I think.
Oh yeah. Yeah. Dominik. Yeah, I should have said that. Dominik Preuss. Yeah, so soon I'll be updating my paper on the archive with this appendix added to it that he wrote.
Are they working with anyone?
Not that I know of. I mean, I'll certainly be talking with him more. I've only
That's amazing.
I mean, I thought this was incredibly insightful, this proof. Even if it's not a huge class of polytopes, I mean, I was just trying to like play around with like, well, what conditions would make things good? But, you know, of course, if instead of requiring every possible directed path never to revisit a face, you really would like to just say that there exists directed paths that never revisit faces, right? I'm assuming a lot, but.
Okay, so let's thank Patricia again.